All right, well, what happens if we have x is approaching infinity? Okay, well, of course, if we were to replace our x's with infinity, we can definitely see that these functions would be increasing, getting larger and larger. So we can see we got another indeterminate form, so that lets us know we are now able to apply this L'Hopital's rule. Okay, so again, what does the rule say? Just simply find the derivative of your numerator and the derivative of your denominator. Okay, so let's see if we can remember the derivative of natural log. So remember, it's just take the derivative of the inside, so that's going to be 4 divided by the inside. Okay, so let's do the same thing in the bottom. Take the derivative of the inside, that's just going to be 10, and divide that by the inside. And of course, the derivative of this 2 here would just be 0. Okay, all right, so we have the limit as x approach infinity, okay, of our, what we're going to call this is a complex fraction, right? So let's see if we can simplify it down a little bit. So we're going to keep the top and then multiply it by the reciprocal of the bottom. Okay, so if you want, you can put parentheses around it, but we're going to go ahead and distribute it, right, to everything here. So what does that become? We now have 40x plus 16 in the top, and then multiply your bottoms together, right? Your 40x plus your 70, okay? All right, so that looks a little bit better. Okay, we don't have so many fractions there. We just now have a regular rational fraction, okay, rational function. All right, well, let's see then if we go ahead and apply our limit again. So what's going to happen, right? If we were to plug in infinity for x, we can definitely see, right, what's going to happen. Top and the bottom both are going to get larger and larger. Okay, so we know, what does that mean? Keep applying L'Hopital's rule. That means you can keep finding the derivative, okay? So now find the derivative of your numerator, find the derivative of your denominator, okay? So of course the derivative of 40x is 40, and then of course the derivative of 16 would be 0. So then in the bottom, derivative of 40x, again, that's 40. And of course, the derivative of 70 is 0. So what do we end up getting? We end up getting 40 over 40. Okay, well, that just simply simplifies to 1. All right, well, apply your limit. Okay, there's actually no x to plug in for, so we know the limit of a number is just that number. So we end up getting 1. All right, so therefore, this limit is equal to 1. Alrighty, okay, well now let's see what happens if we have something like so. Okay, so x is approaching 10 from the right. Okay, you got the little plus sign here, so we know it's from the right. So if we try to do our direct substitution, we can see that as it's getting closer and closer to negative 10, right, you can see that your denominators are starting to approach 0, right? So that means, of course, in the numerator, we have this 1 minus 1. That's going to give us a 0, and then we get a 0 in the bottom. So again, indeterminate form. So that's how we know we are able to apply L'Hopital's rule. Okay. Well, let's see what we should do. Okay, if we take a look at what we have here in the denominator, since they aren't the same, we're not exactly able to subtract them, right? We can't subtract the two pieces because of the we don't have a common denominator. So what we're going to do is we want to try to get rid of our radical over here. So basically, we're going to rationalize the denominator over there on that right-hand side of that, okay? So that means we're going to multiply the top and the bottom over here by the square root of x plus 10. So what do we get? 1 over x plus 10 minus, okay, go ahead and multiply across. And what do we get? Square root of x plus 10. And then, of course, in the bottom, since both of them are the radical, that's just going to become x plus 10. All right, well, what do you notice? We now have the same denominator. Okay, so since we have the same denominator, then we can just simply rewrite that as 1 minus the square root of x plus 10, and then that whole thing now is over x plus 10. Okay, all right, so we're able to rewrite it, and so then don't forget, we now can put our limit in front here to see if we're able to apply. Okay. All right, so see if we're able to apply our limit. Okay, so let's see what's going to happen here. So we know, of course, exactly at -10, if we were to plug in -10 here, we know that would give us 0 in the bottom. Okay, but here we're just really approaching -10 from the right. Okay, so we're getting closer and closer to 10, right, from the right side. Okay, so what's happening then in the bottom? Okay, as we're getting closer and closer to 10, right, we actually end up getting closer and closer to 0. Okay, so the bottom is approaching 0 as x is approaching -10 from the right. Well, same idea is going to happen here, right? As x gets closer and closer to -10, under that radical, we end up getting 0. Okay, well, if we were to put this together, of course, we know the square root of 0 is 0. So 1 minus 0 over 0, 1 over 0. But what do we know that means, right? That means we can say this is the same thing as infinity. Okay, so basically as your denominator is getting smaller and smaller, that fraction is going to infinity. Okay, so we actually end up getting infinity, right, for our limit. Okay, so therefore, we're saying that this limit here is equal to infinity. Okay, so it's okay to get infinity as an answer. And if you end up having 1 over 0, then that means it's approaching infinity.